Well, yeah. So the more energy you create, the more energy you use, the higher the imperative to expand out into the universe. But also not just the imperative, but the capabilities.
Mhm.
And you've kind of, as a side on your lab page, mentioned that you're sometimes interested in astroengineering. So what kind of space architectures do you think we can build to house humans or interesting things outside of Earth?
Yeah, I mean, there's a lot of fun ideas here. One of the classic ideas is an O'Neill cylinder or a Stanford torus. These are like two rotating structures that were devised in space. They're basically using the centrifugal force as artificial gravity. And so these are structures which tend to be many kilometers across that you're
Mhm.
building in space, but could potentially habitat millions of people in orbit of the Earth. Of course, you could imagine putting them, if the Expanse does a pretty good job, I think, of exploring the idea of human exploration of the solar system and having many objects, many of the small near-Earth objects and asteroids inhabited by mining colonies. One of the ideas we've played around with our group is this technology called a quasite. A quasite is an extension. Again, we always tend to extend previous ideas. Ideas build upon ideas. But an extension idea called a statite. A statite was an idea proposed, I think, by Ron Forward in the 1970s. 1970s seemed to have all sorts of wacky ideas. I don't know what was going on then. We had I think the Stanford torus, the O'Neill cylinder, statites, the gravitational lens. People were really having fun with dreaming about space in the 70s. The statite is basically a solar sail, but it's such an efficient solar sail that the outward force of radiation pressure equals the inward force of gravity from the sun.
Mhm.
And so it doesn't need to orbit. Normally you avoid, the sun is pulling us right now through a force of gravity, but we are not getting closer towards the sun, even though we are falling towards the sun because we're in orbit, which means our translational speed is just enough to keep us at the same altitude, essentially, from the sun. And so you're in orbit, and that's how you maintain distance. A statite doesn't need to do that. It could be basically, completely static in inertial space, but it's just balancing the two forces of radiation pressure and inward gravitational pressure. A quasite is the in-between of those two states. So it has some significant outward pressure, but not enough to resist fully falling into the star. And so it compensates for that by having some translational motion. So it's in between an orbit and a statite. And so what that allows you to do is maintain artificial orbits. So normally if you want to calculate your orbital speed of something at, say, half an AU, you would use Kepler's third law and go through that, and you'd say, okay, if it's at half an AU, I can calculate the period by p squared is proportional to a cubed and go through that. But for a quasite, you can basically have any speed you want. It's just a matter of how much of the gravitational force are you balancing out. You effectively enter an orbit where you're making the mass of the star be less massive than it really is. So it's as if you were orbiting a 0.1 solar mass star or a 0.2 solar mass star, whatever you want. And so that means that Mercury orbits with a pretty fast a pretty fast orbital speed around the sun because it's closer to the sun than we are. But we could put something in Mercury's orbit that would have a slower speed, and so it would co-track with the Earth.
Mhm.
And so we would always be aligned with them at all times. And so this could be useful if you wanted to have either a chain of colonies or something that were able to easily communicate and move between one another, between these different bases. You'd probably use something like this to maintain that easy transferability. Or you could even use it as a space weather monitoring system, which we actually proposed in the paper. We know that major events like the Carrington event that happened, can knock out all of our electromagnetic systems quite easily. A major solar flare could do that, a geomagnetic storm. But if we had the ability to detect those higher elevated activity cycles in advance, the problem is they travel obviously pretty fast, and so it's hard to get ahead of them. But you could have a station which is basically sampling solar flares very close to the surface of the Earth, and as soon as it detects anything suspicious magnetically, it could then send that information straight back at the speed of light to your Earth and give you maybe half an hour warning or something that something bad was coming. You should shut off all your systems, or get in your Faraday cage now and protect yourself. And so these quasites are kind of a cool trick of, again, kind of hacking the laws of physics. Mm-hmm. It's like another one of these exploits that the universe seems to allow us to do to potentially manifest these artificial systems that would otherwise be difficult to produce.
So leveraging natural phenomena.
Yeah. That's always the key, is to work, in my mind, it's to work with nature. That's how I see astroengineering, rather than against it. You're not trying to force it to do something. That's why I always think solar energy is so powerful, because in the battle against nuclear fusion, you're really fighting a battle where you're trying to confine plasma into this extremely tight space, or the sun does this for free. It has gravitation. And so that's in essence what a solar panel does. It is a nuclear fusion reactor fueled energy system, but it's just using gravitation for the confinement and having a huge standoff distance for its energy collection. And so there are tricks like that. It's a very naive, simple trick in that case, where we can, rather than having to reinvent the wheel, we can use the space infrastructure, if you like, the astrophysical infrastructure that's already there to our benefit.